So look at these pictures and tell me what is common. Okay, like what scientific phenomenon is common in these three images? Any idea?
I'm not sure.
Okay, have you ever seen this kind of decorative item?
Yes, sir.
Okay, okay. There is a light source at the bottom, and there are some fibers. Okay, and you see light at the tip of those fibers. Okay, the actual light source is here. Does that strike anything? Okay, look at the second image. What do you see in the second image?
Or a reflection type of image on the ground.
What is that called? It's called Mirage. Okay, on sunny days, fine, you can see this on the roads. And third one, like third and fourth, if you see, they are two images of the same scene. One is normal view, the other is called fisheye view. If you have ever noticed in digital camera editing options, you'll have one editing option like this also, fisheye view. Okay, fine. So what is common in all these situations is total internal reflection of light. TIR. Fine. So let's understand what is TIR and how these phenomena take place. Rishi, tell me the formula for Snell's law.
Sir, N1 by mu1 by mu2 is equal to the sine angle of the first one and by the sine angle of the second.
Okay, you can't say first one and second one.
Sine I by sine R.
Okay, repeat. Mu1 by mu2 is equal to?
Sine I by sine R.
Okay, it is sine R by sine I. Okay, you can better remember it as mu1 sine I is equal to mu2 sine R. Okay.
Okay, sir.
Fine. Generally, when light enters from a rarer medium to a denser medium, how does light bend? Rarer to denser.
Towards the medium, towards the normal.
Towards the normal. And reverse, if it goes from denser to rarer, the light ray bends away from the normal. Correct. So consider something like this. Let's say there is a glass slab. Now, glass, is it a rarer medium compared to air or denser medium?
Denser.
Denser. Okay. Air, vacuum, they have refractive index 1. Any other material which allows light to pass through it, light will travel much slower. So refractive index will be more than 1. So glass refractive index is more than 1. And outside is air, whose refractive index is 1. Okay. Now at a particular point of incidence, let's say this one, let's first draw the normal. Rishi, is my voice clear?
Yes, sir.
Okay. Let's first draw the normal and then we will look at different rays undergoing refraction while being incident at that point. Okay. Now, if a ray is incident along the normal, let's say light is incident from the glass, from inside the glass. If a ray is incident along the normal, Rishi, tell me what happens to this ray? Does it bend? If it bends, which way will it bend? Or do you think it will not bend?
Sir, it won't bend, sir.
It won't bend. Okay. Snell's law, mu1 sin I is equal to mu2 sin R. For this particular ray, which is incident along the normal, angle of incidence is 0. Then angle of refraction also will be 0. Okay, it will pass straight without any deviation. Okay. So incident ray is inside the glass slab. Refracted ray, this ray doesn't bend. Okay, but the second medium is air. Fine. Suppose another ray is incident like this. What should happen to this ray? It is originally passing in this direction. What should happen to this ray?
Sir, it should go away from the normal.
It should bend away from the normal. So depending on the refractive index, let's assume it bends like this. Okay. Let us go on increasing the angle of incidence. Now consider a third ray incident somewhat like this. Okay, its original direction of propagation is this. Now this one also has to bend away from the normal. Now compared to the green ray, the blue ray has a greater angle of incidence. Now mu1 sin I is equal to mu2 sin R. I is the angle of incidence, R is the angle of refraction. Now I and R, angle of incidence and angle of refraction, neither of them can be more than 90 degrees. It simply doesn't make sense. Okay, no ray can be incident at an angle more than 90 degrees with the normal. Because at 90 degrees with the normal, the surface will be there. How will the incident ray make more angle than that? Impossible. Same with angle of refraction also. So I and R can never be more than 90 degrees. Okay. So I ranges from 0 to 90, R ranges from 0 to 90. In that range, when angle increases, sine value increases. Because sine 0 is 0, sine 90 is 1. So in the range 0 to 90, as angle increases, the sine value increases. Now for the blue ray, the angle of incidence is higher. Then to maintain equality, the angle of refraction also will have to be higher than the green one. Okay. So the blue ray bends and it bends somewhat like this. It has to refract more than, or it has to bend more than the green ray when it enters into air. Fine. Now you go on increasing the angle of incidence like this. For one particular ray, let's say this one, the refracted ray will travel parallel to the interface. Like angle of refraction becomes 90 degrees. Do you agree with this or not?
Yes, sir.
Okay. This is called grazing refraction. Okay, the refracted ray travels parallel to the interface. Okay, and its angle of refraction is 90 degrees. Fine. And for that angle of refraction, for the angle of refraction to be 90 degrees, there is a particular angle of incidence which is not 90 clearly. Okay, this angle of incidence is called critical angle. Okay, so basically, critical angle is the angle of incidence. Critical angle is the angle of incidence when angle of refraction is 90 degrees. Is it clear? Rishi, any doubt in this?
No, sir.
Okay. Now tell me, what do you think will happen if the angle of incidence is even greater than the critical angle? Say somewhat like this. What will happen to the pink ray, the last one?
Sir, will it like reflect? Like you can, like it won't go to the medium, only a part of it will go, but some part of it will be reflected also.
No, what did you say? Can you repeat?
Like when it's going, since it already reached more than the critical angle, it will come back in, like, it will come
Ah.
back into the.
It will bounce back into the same medium from which it is incident. And basically, bouncing back into the same medium means undergoing reflection. So it doesn't refract, it gets reflected back into the first medium. Okay, this is what we mean by total internal reflection. And it follows the laws of reflection. Okay, so if a ray is incident on an interface at an angle greater than the critical angle, the ray will be reflected back into the first medium. Complete reflection will take place. That's why it's called total internal reflection. Is it clear?
Yes, sir.
Okay, fine. So critical angle is the angle of incidence for which angle of refraction will be 90 degrees. If angle of incidence is anything more than the critical angle, refraction cannot even take place. The energy, the light energy will come back into the first medium. The light will come back into the first medium. So it's basically bouncing off the interface. That is nothing but reflection, not refraction. Okay. So suppose the refractive index of the first medium is mu1. Okay. Glass slab refractive index, let it be mu1. And second medium, let's call it mu2. Okay. Whether it is air or any other medium, let's call it mu2. Now, for TIR, total internal reflection, to take place, it is necessary that the ray has a tendency to bend away from the normal. If it tends towards the normal, angle of refraction can never become 90 degrees. Why? If the ray has a tendency to bend towards the normal, as I increases, R increases, that's fine. But R should be smaller than I towards the normal, no? So it should be smaller than I. So even if angle of incidence becomes 90 degrees, angle of refraction is not going to become 90 degrees. Is it clear? When light is
Yes, sir.
incident from rarer to denser, TIR cannot occur. Okay. Only when it is incident from a denser medium onto a rarer medium, total internal reflection is possible, because in this case, it has a tendency to bend away from the normal. Okay. So denser to rarer means mu1 should be more than mu2. Only then TIR is possible.
Sir, 1 second. Can you scroll up? I'll just
Okay.
write it down.
Yeah. Like in your notebook, if you want to indicate different rays, then the second one you can take 2 arrows. Here also 2 arrows. Third one, which is the blue one, 3 arrows, and show 3 arrows here. Fourth is the red one, 4 arrows for it. And 4 here also. And then the orange one, you can put 5. If you have different colors, you can use. Otherwise, you can do it this way.
Sir, does critical angle change with the medium, like material of the medium?
You will answer that question. Let's see. We have found that TIR is possible, or we have concluded that TIR is possible only if mu1 is more than mu2. Okay. Now you are asking about critical angle and whether it depends on the medium. The only equation we have which can include that angle is Snell's law. Okay. So what did I say? Critical angle is the angle of incidence when 90 degrees is the angle of refraction. Okay. So in place of I, you substitute theta c, and in place of R, you substitute 90 degrees in Snell's law. Tell me what you get. Okay, I'll write Snell's law here. Mu1 sin I is equal to mu2 sin R. Substitute theta c in place of I and 90 degrees in place of R. What does the equation change into?
Mu1 sine theta c is equal to mu2.
Okay. Mu2 sin 90. Sin 90 is 1. Good. Okay, wait. Theta c. Therefore, sine theta c, sine of the critical angle, becomes mu2 divided by mu1, or critical angle becomes sine inverse mu2 by mu1. Now, what are mu2 and mu1?
Sir, mu2 is the uh, medium where the ray is traveling to, and mu1 is
mu2 is
the
the what of the medium?
refractive index.
Refractive index. Okay. So now you tell me, do you think critical angle depends on the two media or not?
Yeah, sir, it does.
Okay. Sine inverse mu2 by mu1. So it definitely depends. Fine. In fact, in this chapter itself, in the next part of this chapter, you will learn the different colors of light. Okay. That is different wavelengths have different refractive indices for the same medium. Okay. Like you can't say glass has a fixed refractive index of 1.5. For one color, it may be 1.5. For another color, it may be 1.52. Okay. So refractive index of a medium can change based on the wavelength. It will change based on the wavelength. Okay. So total internal reflection can happen only for few colors also, depending on refractive. We'll get into those details later. For now, you assume one medium has one refractive index. So for two media, one of them having refractive index mu1, the other one having refractive index mu2, irrespective of which color is incident, the critical angle is sine inverse mu2 by mu1. Okay. Right. So if the angle of incidence is anything more than this, the ray undergoes total internal reflection. Now solve this problem quickly. Refractive index of glass is 1.5, that is 3 by 2. Refractive index of water is 4 by 3. So Rishi, tell me, if we want total internal reflection between glass and water, from which medium to which medium should the ray be traveling?
Density error, so glass to water.
Glass to water, correct. This is 1.5, this is only 1.33, right. Derive the expression for critical angle for glass water interface. I mean, derive the critical angle, not expression. Any answer?
Just a minute.
Okay. Okay. Tell me the formula that you use to derive critical angle.
Theta c is equal to sine inverse of mu2 by mu1.
Okay. Now, the next thing you need to think is which medium's refractive index to take mu2 and which one to take mu1. How have you taken?
Sir, I took 4 by 3 as mu1.
Why?
Oh, that's where I went wrong.
I didn't tell you whether your answer is correct or wrong. But anyway, why did you?
No, sir.
Huh.
But I'm supposed to take the one which is traveling towards mu2. So
Huh. So incident ray should be in the medium of refractive index mu1. Refracted ray will be in mu2. And we are talking about total internal reflection. No, critical angle is related to that. So it should be going from denser medium to rarer medium. So denser should be mu1, rarer should be mu2. They don't have to tell you that. You can like conclude that on your own. So it should be sine inverse of rarer is mu2, that is water. Denser is mu1, that is glass. So that becomes sine inverse 8 by 9. Some angle you can find out using the calculator, but do that later. Okay, so that is the critical angle for glass water interface. You can be asked critical angle for air glass interface, air water, any two media can be given. So will you be able to calculate or not?
yes, sir.
Okay. Fine. So if a ray is incident from a denser medium onto a rarer medium at an angle more than critical angle, it bounces back into the first medium. That phenomenon is what we call total internal reflection. Fine. Now consider this glass slab itself. Okay, let's say it's a wide glass slab. Assume there is a small dot, okay, or a small particle inside that glass slab. Let's say it is green in color. So there's an actual something present there, actual particle present there. Now from that particle, see, this is glass, light can enter into glass. So maybe there's, suppose the lights in the room are switched on, light falls on that particle and light from that particle gets reflected in all directions. Usually that is how we see things, no? Light from a source falls on an object, gets reflected. The reflected light, if it enters into your eye, you will be able to see it. So from this particle, imagine light rays emerging in all directions, or light rays being reflected in all directions. Okay. So tell me, the light ray coming from the particle, or light ray incident from the particle in this direction, what happens to it? Will it bend or not? Or instead of particle, you assume there is a small bulb present there. Okay, very small bulb. We'll consider it as a point source. So bulb will be emitting light in all directions. So some light will be traveling this way. Rishi, tell me what happens to the ray which travels like this?
Sir, it won't deflect.
It won't bend, passes straight. Okay. Because it undergoes normal incidence, it passes straight. Fine. But there are many other rays also, no, which will be emerging from the light bulb. So consider this ray, which is incident at an angle. What happens to this one? It is going from glass into air.
It will go away, sir.
It bends away from the normal. Right. Consider another ray incident like this. What happens to this one? Bends away from the normal, right? So just a moment. Maybe bends like this. Okay. And take another ray to maybe somewhere here. If the angle of incidence is more than the critical angle or is equal to the critical angle, it undergoes grazing refraction like this. All other rays which are incident beyond that distance, okay, for example, this one, this won't even enter into air. It will bounce straight back into the glass itself like this. Same thing happens with every other ray which is incident at an angle more than the critical angle. Are you getting the picture?
Yes, sir.
Okay. The same will happen on the other side also. And now I will remove this bulb. We will think of it as a point source or a point object. Okay. Single point object. It emits waves. It emits light in all directions. Okay. The same pattern will be seen on the other side also. And in fact, see, this is the cross-sectional view that we are taking. The glass slab has a surface, right? It's like a table surface. Bulb is under the table. Okay. So what is happening effectively? The light from the bulb is coming out of the table only within this distance. Beyond that, the light from the object is not entering into air. Okay. So whatever light comes out, if you imagine this as a tabletop surface, you will get a circular region like this, through which light comes out of the glass slab. Rishi, are you able to picture that or not?
Yes, sir.
Okay, same thing will be happening on the other side also. In fact, you have to imagine in 3 dimensions. So it's like a, what do I say? Flower vase maybe. Yeah. Outside that circle, no light from the object will be entering into air. Okay. So if there's a person somewhere here, if there's an observer looking from this angle, the observer will feel the light is coming from somewhere here. If there's an observer here, this observer will feel the light is coming from somewhere here. Okay, so they'll perceive different apparent depths. Depending on the observer, the apparent depth can change. Now, okay, don't be surprised. Like we had derived one formula for apparent depth. Apparent depth is equal to actual depth into mu2 by mu1. We never cared about where the observer was present. We had a fixed formula for apparent depth. Now I'm saying for different observers, the apparent depth will be different. Okay, that is because this formula was derived using the spherical surface refraction formula. Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. And when is this valid? Only for paraxial rays. Means rays must be very close to the principal axis. That means, see, some rays will be reflected this way, refracted this way, no, very close to the principal axis. If there's an observer here, to that observer, this will be the apparent depth. Okay, but to all observers, it won't be the same. And you don't have to bother much about it. Exact apparent depth derivation for each observer is not necessary at this point. Okay. So from the point source, which is present below the interface, light will be going into the outer world or in the second medium only through this circle. Is that clear? Any doubt in this?
Sir, so the only part where we can see the reflection is from that specific black part.
Refraction.
Yes, sir.
Yes. Suppose there are many different people looking at this table, okay, or looking at this glass slab. To all of them, the light from the source, see the source, you can think of it as a small bulb. All of them will see a small bulb present within this circle. Clear?
Yes, sir.
Actually, you can try also. You can try this with water. Like you can take a large container of water. Okay. Keep a coin or something, some bright object at the bottom of the container. Then you will see that, you will notice that you will be able to see that object on the surface of water. Like water, you can see things through water, right? But that object which is at the bottom of the bucket or the container will only appear within a circle on the surface of water, not beyond that, from wherever you look at it. Is it clear?
Yes, sir.
Fine. So suppose this object is at a real depth, capital D. Okay. And this medium's refractive index is mu1. The outside medium's refractive index is mu2. Okay. Rishi, use some logic and try to derive this distance, the radius of the circle through which the object can be seen by the outside world, or object can be seen by an observer in the second medium. I want you to derive an expression for R in terms of capital D, mu1 and mu2. Try. Rishi, any answer?
Sir, I'm not sure.
Okay. Any idea that can be applied in this situation? You have to find out the radius of the circle through which light enters into the second medium. Okay, Rishi, tell me what is special? See, radius is determined by this last ray that undergoes refraction, right? After that, you will get total internal reflection. What is special about this ray? Or what do we know about this particular ray?
Sir, that it's exactly,
Exactly.
it's like the same line as the medium, the difference between the mediums.
Mhm. Like we can see it is going parallel to the interface. That's fine. Any quantity we know about that ray? When will light bend like that?
When it's, the angle is 90 degree,
Which angle is 90 degree? What do you call that angle?
critical angle.
Angle of refraction is 90 degree. Okay.
Yeah,
For that, the angle of incidence is called critical angle. So this is the critical angle. Fine. And if that angle is the critical angle, then this should also be theta c. Do you agree with this or not?
yes.
Okay. Now we see a right angle triangle here consisting R capital D and the critical angle. Okay, I'm pasting the right angle triangle on the right side. So this distance is the R that we are looking for. The blue one is R, the vertical one is D, and the angle between them is the critical angle. Yes or no? How are these three related now?
Sir, r square plus d square is equal to the,
We want to involve the angle. Why we want to involve the angle is because we have a formula for critical angle in terms of mu1 and mu2. So relate R capital D and refractive index. Sorry, R capital D and the angle. A simple trigonometry for the angle capital D is the adjacent side. R is the opposite side.
sir, cos.
No,
Mm. Oh my God.
this is the opposite side to the angle.
Oh, tan.
And this is the adjacent side. So tan theta C is equal to R divided by D. Okay, fine. Now we want the answer in terms of mu1, mu2, not critical angle. If critical angle is known, then this is it. Okay, but we want the answer in terms of mu1 and mu2. How is critical angle related to mu1 and mu2?
Sir, sine inverse is equal to mu 2 by mu 1.
Sin theta C is equal to mu2 by mu1. Okay. Theta C is sine inverse of mu2 by mu1. So sin theta C is mu2 by mu1. If sin theta C is this much, how do you get, like if you know sin theta, how do you derive tan theta? If you know the value of sin theta, how to derive tan theta?
Sir, tan is just opposite by adjacent and sine is opposite by hypotenuse.
Hmm. Okay. See, tan is sine by cos. If you know sine, then cos is under root 1 minus sine square. So 1 minus mu2 square by mu1 square can be written as under root mu1 square minus mu2 square whole divided by mu1. The denominator mu1 is outside the root. Is this clear?
Yes.
Now you divide sine cos, you'll get tan. Therefore, sine divided by cos, if you do, it's like mu2 by mu1 divided by this whole thing. Mu1 gets cancelled upon division. Tan becomes mu2 by under root mu1 square minus mu2 square is equal to r divided by d. That way you can derive r in terms of mu1, mu2 and d. Okay. This analysis and derivation are important. This is there in NCERT also actually. This concept. Is it clear?
Yeah.
Okay. So if there is a point object inside the glass slab, then to the outside world, it will appear only inside this circle, through this circle. Okay. Now you visualize things in reverse. Just a moment. Suppose this is a water tank, okay, or an aquarium tank. Okay. So all this is water. Outside is air. Okay, water is denser than air. That's fine. Okay. Now imagine, see if an object O is present here, if a point object is present here, light from this object will enter into air through that circle. The other light will get reflected back into the water. Okay, I'll remove those rays. The rays that get reflected back into water, I'm not showing. Okay. Situation will be like this. Now, if the direction of these rays is reversed, what do I mean to say? Suppose a ray is incident at an angle almost 90 degrees like this. Then it will bend and reach this point. Obviously, the ray has to retrace its path. Okay, you just have to apply Snell's law in the opposite direction. You will see that it follows this path. So what does this mean? All the light from the outside world, okay, all the light from outside the aquarium or above the aquarium reaches this point through this circle itself. Rishi, are you getting the picture or not?
Yes.
Okay. Let me just complete this. All the objects that are present outside the aquarium, above the water level, the rays from those objects will be reaching this point through this circle itself. And this is what we call fish eye view. Suppose there is a fish inside this water tank, okay, or aquarium. You visualize a fish here. Fine. The fish's eye, you can treat it as a single point. Okay. Let's say the eye of the fish is here. So if the fish looks up, what happens is whatever is present outside the aquarium, okay, whatever is present above the aquarium in the outside world, it will see an image of all that within that circle. Okay. Now see, when you look up, you get a large view, right? In fact, your entire field of view will be filled by whatever is present. Okay. Imagine shrinking all that view into a circle of limited radius. That is what we call fish eye view. That is what I had shown you here. Okay. See, when you look at things normally, let's say this is the picture that you see. Okay, you see their proper orientation, proper size and all. You can get an idea of their proper size and all. Okay, but imagine shrinking that image into a circle. It becomes like the one that you see on the left. Yes or no?
Yes, sir.
This is what we call fish eye view. And even humans can observe this if you go underwater and look up. But there are a lot of constraints. The water surface must be perfectly calm. Only then you will see the outside world in a proper circle. Okay, so it's difficult for us to actually observe this. You can try it with a camera if you want. Okay, if you have a waterproof camera, just put it inside a water container, fill it with water up to a certain height, and like you should set a timer or something such that the camera clicks when the water surface is calm. Then you will see that in the photo, all the outside world will appear within a circle itself. Now, what will appear outside that circle? What will the fish see outside that circle? Whatever is inside the aquarium, it will see that. What I mean is, suppose this is the aquarium. Let's say there are some stones here. Okay. Then consider one ray from this stone incident like this. If this angle is more than critical angle, the fish will see, this ray gets reflected this way. Okay. So outside the circle, what the fish sees is a reflection of all that is present here. Is it clear? Because light from those sources will be incident at an angle more than the critical angle, and it undergoes total internal reflection and reaches this point. Got it?
Yes, sir.
Okay. So yeah, that is why I showed you this as an example or as a situation where total internal reflection is applicable. Okay. Next is mirage formation. Now, what do you see in that picture? There is a car on a road, and it seems like the road appears to behave like a mirror, as if there is water on it. Usually water surface, it behaves like a mirror. Okay. So here the road appears to behave like a mirror. Why do you think this happens? Okay, suppose this is the road. And mirages you will mostly observe on very sunny days on roads. Okay, the temperature has to be high. The road surface temperature has to be high. So what happens is when the road surface is very hot, okay. Now what is above the road? Air. Okay. Air is the medium through which light is traveling above the road. The layers of air which are close to the road, their optical density will be less. And as you go higher and higher above the road, the air density will increase. Okay, air's optical density will increase. So the optical properties of air will change depending on its temperature. Okay. So let's consider some layers of air above the road. Assume this is one layer. This layer's optical density is the least. As you go higher, the optical density increases, means refractive index increases as you go higher. So let's consider maybe 3 to 4 layers. Actually, it varies continuously. You won't even see such a thick layer having one refractive index. But for our understanding, we'll consider it like this. Okay. Now, what is happening here? You feel as if there is something present here. Okay, you are seeing an image, right? You are seeing a reflection of that car. Means rays are entering into your eye from that angle. Okay, let me mark a point here. Let's say this one. Let's call this as P. Light is somehow entering into your eye from that angle. But actually, where is the light coming from? Light is coming from the car. We are able to see the car. Okay, light is entering into our eye directly from the car, but there is some more light entering this way. Light is undergoing reflection. From the car, it is falling on the road and bouncing back into our eye. Okay, that is what it appears like. The road appears like a mirror, but the road is not actually a reflecting surface. It's a very rough surface, in fact. Then how does this happen, or why does this happen? Let's see. Suppose the observer is somewhere here. Okay, let's say there's an object somewhere here, very far away. Okay, you can see in that image, this is a very good image, a picture actually. You can see that there's no reflection happening in this region. Only at far distances you will be able to see, you will be able to feel the road as a mirror. The road which is immediately in front of you, it won't look like a mirror. Rishi, have you ever observed this in real life or not?
Yes, sir.
So suppose there's a distant object like this, like that car. Instead of car, I have taken an orange dot. It's a point object. Now from that object, some light will be entering directly into your eye like this. Okay. That light enables you to see the actual object, like how you see the car in that picture. That's fine. But see, from this same source, from this same object, light will be light will be traveling in many different directions, right? So imagine some light which goes downwards. Now, what happens to the density of air as you go down? The optical density decreases. Okay. So the layer which is next to the road is the rarest in terms of optical density. As you go up, the density increases. So this is the densest layer of air. As you go down, you will go to the rarest layer of air. So refractive index is high here. Refractive index is low here. Okay. Now for the light ray which is going downward from the object, like this, towards the ground, it is incident from a denser layer of air onto a rarer layer of air. Yes or no?
Yes.
Okay. Now you consider an angle of incidence here. Some angle of incidence will be there, and it should bend towards the normal or away from the normal. It's going from denser to rarer.
Sir, away.
Away from the normal. So this ray was actually traveling in this direction. Now at the first surface itself, it has to bend away from the normal. So maybe bends like this. Okay. Now what is happening? The angle of incidence is increasing further. As the ray goes deeper and deeper, the angle of incidence increases. You can call this first angle as I1. Second angle is I2. I2 is more than I1 because the ray had bent away from the normal. Yes or no?
Yes.
Now the second ray is traveling like this. But when it goes to another layer of air, another rarer layer of air, it should further bend away from the normal. So assume it bends like this. Then here, the angle of incidence will be even higher, I3. And it's possible that this angle of incidence is more than critical angle. And once it becomes more than critical angle, what happens? The ray bounces back into the same medium. Total internal reflection. Again, it bends towards the normal. Bends towards the normal. This is what happens. So yeah, I should take the observer here. Now there is one ray reaching the observer directly from the object. So the observer will be able to see the original object. But there is one ray reaching the person's eye at an angle like this. So you will also feel that there is something present here on the road, or you will see a reflection. Did you understand how mirage formation takes place?
Yes, sir.
Okay. The main reason is the variation in optical density of layers of air. So Rishi, tell me, the layers closer to the road, are they rarer or denser? The layers close to the road, are they rarer or denser?
They're denser.
It's written on the screen.
Sir, but
layers close to the road
oh
are
yeah, sir.
rarer. Okay, as you go higher above the road, they become denser. Okay, so light from some object, if it is going downwards, it is going from denser to rarer layers. So it bends away from the normal, bending away, and away. At one layer, it undergoes total internal reflection and then starts coming up. Okay, so if an observer sees that ray, then the observer will feel that the observer will see an image on the road. That is what is the mirage that you see. Is it clear?
Yes, sir.
Okay, so that explains mirage formation. It is also due to total internal reflection itself. Next, we are left with these tubes. Okay, basically what is happening here, there are many tubes. I can show you one of them. Maybe visualize a tube like this. Fine. At one end of the tube, there is a light source. There's a bulb. And you see light coming out from the tip of the tube. Okay, light is coming out from here. The tip of the tube will be glowing. Fine. So basically what is happening, light from the source is bending along this tube or is traveling along this tube and is coming out from here. It's not coming out anywhere in between. Okay. It's not coming out from the sides of the tube anywhere. It's only coming out from the other end of the tube or the other end of the fiber. Rishi, what are such fibers called? Which help light go from one end to the other end without leaking out in between. Okay, the fibers or cables used for what do you call broadband connections? What are they called?
Fiber net, sir.
But what is the technical name given to those fibers? The internet, that kind of internet connection is called fiber net. What is that kind of cable called? It's called an optical fiber.
Oh yeah, sir. Yeah.
Okay. Fine. So basically, optical fiber is a what do you say? It's just a substance, okay, material, which behaves like not which behaves like it's a material into which if light enters from one end, it can only leave from the other end. Okay, it doesn't leak through the walls of the material. Okay. So how does that happen? Let's see. Okay, let's consider that glass itself. Glass, or think of it as some material. Okay, some flexible material you can take, which allows light to pass through it. Okay, so there's some medium here. Are you able to observe it? Gray color.
Yes, sir.
Okay. Assume outside the refractive index is N1 and inside, the material's refractive index is N2. It is a solid material. It's not an empty tube. It's like a what do I say? It's completely filled. Okay, it's not empty inside. You can think of it like what? Wait, straw is empty inside. Think of it like a stick. Okay, fine, which can be bent. I'm not getting the correct word for it. Let it be. Now, assume some light is incident. Assume some light is incident at this point P. We'll take P as the point of incidence. Okay. See, if a ray is incident along this normal, Rishi, tell me, how is it going to pass?
Sir, it won't deviate.
It won't deviate, it will pass straight anywhere. Okay, so that ray is not of much interest to us. Imagine a ray incident like this. What should happen to this one? Okay, wait. N2 is greater than N1. Inside, the refractive index is more than outside. So outside is rarer, inside is denser. Light is going from rarer to denser. What should happen? The original direction of propagation of light was this. Okay.
So towards the normal.
Rarer to denser, it has to bend towards the normal. Okay. Assume this ray bends towards the normal and passes like this. Okay. As long as it's in the same medium, it will travel straight. But again, you can see that there is some incidence happening here. The light is incident from that denser material onto a rarer medium. Yes or no?
Yes, sir.
Huh. Now, when light is incident from denser medium onto a rarer medium, what happens?
Away from.
Should bend away from the normal. And it's also possible that it undergoes total internal reflection. Yes or no?
Yes, sir.
When going from denser to rarer medium, TIR is possible. And when is TIR possible? When this angle is greater than critical angle. So assume that is what happens. If that angle of incidence is more than critical angle, this ray will not enter into the second medium at all. It will come straight back into the, no, sorry. This ray will not go out through the wall of the container. It will come straight back like this. Okay, it won't go out through the wall of the fiber. Yes or no?
Yes, sir.
This is what happens inside an optical fiber. Okay, it will keep bouncing off the walls of the fiber till it emerges out at the other end. Even if you bend the fiber, it won't matter much. Is this clear? And this is how internet communication takes place these days. And all signals are electromagnetic waves. They undergo total internal reflection. Not exactly light, but some electromagnetic waves. Okay, and whatever is the behavior of light, same will be the behavior of other electromagnetic waves as well. Okay. Any doubt in this?
No.
Okay. Now see, the ray which is incident along the normal, it would have passed straight without any deviation. Okay, that's fine. And this blue ray, it is incident at some angle. This angle is greater than critical angle, so it is undergoing total internal reflection. That is also fine. Let's increase the angle of incidence. If you increase the angle of incidence, okay, outside, then what will happen? The original direction of propagation of this green ray was like this. Then after bending, maybe it will go like this. Okay. Now, inside the optical fiber, tell me how this angle of incidence of the green ray is related to angle of incidence of the blue ray. Which one is greater? Inside the optical fiber, which ray's angle of incidence is greater? Green or blue?
Sir, inside blue is up. Blue.
Blue is greater, right? Okay. Now for TIR, total internal reflection to occur, do you need the angle of incidence to be as greater as possible or not? I'm removing the orange one. For total internal reflection to happen, should that angle of incidence, okay, this one or this one, should be as greater as possible or not?
Yes, sir.
TIR will occur only if angle of incidence is more than critical angle, and the higher it is above critical angle, the better. I mean, the safer you can say. Okay, the more sure you can be of TIR happening. So basically what happens is, as you increase the original angle of incidence, the second angle of incidence decreases. So there is a chance that TIR may not happen at the over here. Like for example, the blue ray is incident at a sufficiently large angle there. So let's say TIR is happening. Okay. But the green ray is not incident at such large an angle. So it's possible that the angle of incidence there is less than critical angle, and then it won't undergo total internal reflection. Yes or no? Is that possibility there or not? Okay, just a moment. Yeah, Rishi, are you able to see my screen?
Yes.
Okay, so what I was asking is it possible that the angle of incidence of the green ray at the second surface is less than critical angle or not?
It is possible, sir.
It's possible. Okay, and if it is less than critical angle, total internal reflection won't happen. So what you have to do is you have to choose refractive index in such a way that for no ray, the angle of incidence, the second angle of incidence becomes becomes less than critical angle. Okay. Now see, as you increase the original angle of incidence, the second angle of incidence is decreasing. Rishi, did you observe that or not?
Yes, sir.
Okay. Now the original angle of incidence can be increased up to a maximum of almost 90 degrees. Like this. And if the original angle of incidence is 90 degrees, the ray bends towards the normal a little bit like this. Okay. And strikes the second surface this way. Now this red ray has the least second angle of incidence. Yes or no? Out of blue, green and red, is the red one having the least second angle of incidence or not?
Yes, sir, it does.
Okay. If that angle is more than or equal to critical angle, then the green one and the blue one will definitely be more than critical angle.
Yes, sir.
Okay. So we will derive a condition based on this. The refractive index inside the optical fiber is N2, outside is N1. Now first you tell me, how much is sine theta C?
Mu2 by mu1.
So here it should be, think very carefully. Should it be N1 by N2 or N2 by N1? For total internal reflection to happen inside the optical fiber.
Sir, N2 by N1.
Why?
Sir, because N2 is more than 1 second, sir. N2 is more than that, so it should it should be going from the thing to that thing. So yeah, N1 by N2, N1 by N2.
Correct. N1 by N2. Because the ray which is about to undergo total internal reflection, TIR, is going to happen over these points, right? At that surface. There what is happening? Light is incident from N2 to N1. Okay. Anyway, you got the idea correct. Like you were thinking of which one is greater, which one is lesser, and based on that you are answering. That is even better actually. So here in this case, sine theta C should be N1 by N2 because N1 is that of the second medium, N2 is that of the first medium. Got it?
Yes.
Okay, you gave that answer anyway. I don't have to ask you if you got it. Now that angle of incidence there, I, should be more than this. Then the red ray will not get refracted. It will undergo total internal reflection. Then the green one, blue one, every other ray will undergo total internal reflection. No light can escape from the optical fiber. Let's derive a condition based on this. For that, I will have to enlarge this diagram. Okay, just a moment. What is the first angle of incidence of that red ray? Okay, fine. Let us zoom into this. I'm asking you for that red ray, how much is this angle?
Sir, it's somewhere near 87, 88, 89.
90. Okay, it's just less than 90. You can't tell the number which is immediately less than 90. Okay, so we'll approximate it to 90. Is that okay?
Yes, sir.
Fine. Now, this angle here, we want it to be critical angle. Actually, slightly greater than critical angle, but for the limiting condition, we'll assume it is equal to critical angle. Okay. Rishi, is that fine?
Yes, sir.
Now, if that angle is critical angle, simple geometry, this angle will also be critical angle. Yes or no?
Yes, sir.
Okay. And if this is critical angle, how much is this?
Sir, in terms of like N1 and N2.
No, in terms of theta c only I want. Like suppose critical angle is 10 degrees. How much is this remaining angle?
80.
90 minus theta c. Correct?
Yes.
Okay. Now, why am I bothered about that? Because that angle 90 minus theta c, I'm showing you in this diagram, is the angle of refraction of the red ray when angle of incidence is 90 degrees. Are you getting that?
Yes, sir.
So we'll be able to apply Snell's law now. And 90 minus theta c is the angle of refraction when angle of incidence is 90 degrees from outside medium into the optical fiber. Let's apply Snell's law. Light is going from out. This is the first incidence, not the second one. First incidence. First incidence, light is going from outside. So N1 sine I is equal to inside N2 sine R. And R is nothing but 90 minus critical angle. And what is sine 90 minus theta generally?
Cos theta.
Correct. Therefore, cos theta c should be equal to N1 by N2. Now let's go back to our basic equations. Now we know sine theta c is N1 by N2. Wait, what did we get? Mu1 sin I is equal to mu2 just a moment. For critical angle between optical fiber and outside. Yeah. Fine. So we got cos theta c is equal to N1 by N2. And here earlier, for the critical angle between optical fiber medium and the outside medium, we got sin theta c is equal to N1 by N2. Are these two equations clear?
Yes, sir.
Okay. That means cos theta c and sin theta c must be equal. Both are N1 by N2, right? When will that happen? When is cos of an angle equal to sine of the angle?
Sir, when one is 0 and one is.
What are you saying? This is valid when angle is 45 degrees. Cos 45, sin 45 are both 1 by root 2. Okay, so the critical angle must be 45 degrees. Got it?
Yes.
That means n1 by n2 should be 1 by root 2. That means n2 should be root 2 times of n1. Okay, this is an interesting result. What is n2 in this entire discussion? What is n2 here?
Sir, N2 is the refractive index of the glass.
Fiber, refractive index of the optical fiber. Okay, and n1 is the refractive index of the medium outside. So if n2 is root 2 times of n1 or anything greater than that, okay, all the light entering into the optical fiber will leave from the other end itself. No light will escape from the walls of the fiber. Every ray will undergo total internal reflection at the walls. That is what we have just proved. Got it? Because if that red ray is undergoing total internal reflection, then definitely every other ray will undergo total internal reflection. Yes or no?
Yes.
So we took that red ray and we derived a condition between n1 and n2. And we got n1 is equal to root 2 times, sorry, n2 is equal to root 2 times of n1. The density of the fiber should be root 2 times of density of outside material. Is it clear?
Yes, sir.
If that condition is satisfied, the red ray, which is the last incident ray, extreme case, that itself won't escape from the walls of the optical fiber. Then no other incident ray can escape from the walls of the fiber. Okay, so remember, for an optical fiber to function properly, for any incident ray, okay, its refractive index should be root 2 times the refractive index of the medium outside. N2 should be root 2 times of N1 or greater than that. Is it clear?
Yes.
Okay. So suppose outside medium is air. Suppose N1 is 1. Okay. Means outside the optical fiber is air. Then N2 should be root 2, 1.414 approximately, or greater than or equal to root 2, I can say. If you take a material with that much refractive index, it will behave as a perfect optical fiber. Clear?
Yes. Yes, sir.
Okay. But see, many times what happens, suppose this itself is the optical fiber. Okay. Now, fibers are prone to external damage. Okay. Suppose something hits the fiber from outside, then it may develop a dent like this in its surface. Its surface may not be perfectly smooth. Okay. If something hits it from outside or something falls on the fiber and it gets uh, what grooved a little bit. So usually what they do is they cover this optical fiber. Okay, let's say this is the actual material through which light passes. So usually what they do is around this material, they coat another material, which is also flexible. Okay. Have you ever seen internet cables like outside your home or anywhere on the road?
Yes, sir.
What color do they appear?
White.
White. Okay, yeah, possible. Yes, yes, yes. Some of them are white and mostly black also. That's fine. But that's not the actual material through which light passes. The white coating that you see, do you think it's a material which allows light to pass through it? Does it feel like that?
No, sir, not really.
No, it's not a material which allows light to pass through it. Okay, so that is just the coating. Inside there will be the actual optical fiber material. Okay, the actual material which can allow light to pass through it. Okay, so this actual material which allows light to pass through it, let's say its refractive index is N2, This is called the core. And the surrounding coating that is given to protect the optical fiber region, okay, that is called the cladding. Its refractive index should be taken N1 now, not air's refractive index. Why? Because when light is incident here, it is incident on the core cladding interface. It's not incident from core onto air. Got it? This is where total internal reflection takes place. Therefore, refractive index of the core should be more than or equal to √2 times refractive index of the cladding. Got it? Now, even if there is any external damage, the cladding surface will get dents, but the actual surface where TIR takes place will still remain smooth. Are you able to visualize that or not?
Yes.
So the optical fiber will function safely. So that cladding is like a protective layer. Fine, that is all you need to know about optical fiber. So this is what is total internal reflection and how we make use of it and how some things in nature happen because of it. Okay. Next class we will discuss about refraction by a prism, refraction of light by a prism.